TI-DLP team.
Hello everybody, my name is Cass Kaiser. My partners are Bonron Kush, Rock Grove, and Jake Sal. The objective of our project was to understand the effects of high electric fields on dielectric devices in dielectrics in MEMS devices. Before I go further, I want to give a little background on dielectrics. Dielectrics are materials that act as insulators, meaning they resist the flow of electrons. When a dielectric breaks down, it no longer acts as an insulator, but as a conductor. To understand the effects of high electric field on dielectric devices, we need to perform two main tests, TZDB, time zero dielectric breakdown, and TDDB, time dependent dielectric breakdown. TZDB requires us to apply an initial voltage to dielectrics and then ramp this voltage up until breakdown has been achieved. Time dependent dielectric breakdown testing requires us to apply a constant voltage to the dielectric and then measure the breakdown as a function of time. The constant voltage we apply to our dielectrics in the TDDB test actually varies, and it really depends on us and how quickly we want the dielectric to break down. We decided, in order to get a firm grasp on the effects of high electric fields on the dielectrics, we decided to run several tests at 80%, 70%, 60%, 50%, and 40% of our time zero dielectric breakdown voltage. To perform this test, we constructed a PCB which consists of three main parts. There's an ammeter, which is capable of measuring the leakage current accurately down to 1 picoampere. There's a microcontroller, which acts as the interface between our PCB and our lab algorithm. And there is a boost converter, which accepts an input voltage of 30 volts and outputs a voltage all the way up to 324 volts. Now, our PCB design was able to collect data on up to 6 dielectrics simultaneously. The lab algorithm actually runs the test and controls everything that is necessary in the test. It controls the output of the boost converter. It collects data from the ammeter, and it also records the time and voltage of breakdown at breakdown. Now, the way breakdown is detected is when the test first starts, a reference current is established within the first 15 seconds, and the leakage current is constantly monitored and compared to this reference current. If the leakage current is exponentially greater than this reference current, then breakdown has occurred. If not, then a new reference current is established every minute afterwards, and the process repeats itself. Now, once breakdown has been detected, the time and voltage at breakdown is output to an Excel spreadsheet for analysis. Now, why would we do this? Because there's all equipment out there, namely a probe station, that is capable of collecting this data, capable of measuring and performing these tests. Well, two main reasons. One, the probe station can only collect data on 1 dielectric at a time, whereas our PCB can measure and collect data on up to 6 dielectrics simultaneously. And more importantly, a probe station costs $100,000 and our test cell costs $650 and can be more cost effective if manufactured in bulk. As far as who did what this semester, Bonron and Jake focused on the PCB design, Rock Grove focused on developing the lab algorithm, and Bonron and I did the troubleshooting on PCB. I also handled the financial aspects and the item procurement for PCB. Thank you for your attention. On that, I hand it over to our panelists to answer any questions.
Did you have an opportunity to look at the temperature effects?
No. That was not that important to TI for this project, so.
Sentence or two on what you had seen design 1 and 2. You showed 2 images there on how the design changed.
Are you asking what's the difference?
Yeah, just highlight what were the main
Well,
steps.
the first semester it was kind of just manual. We did it in a breadboard. The second semester we constructed a PCB. Everything the interconnects are completely hardwired and everything is soldered into the board, so it's much more legitimate, I guess. Any other questions? No? Thank you.
Thank you very much. Amber was the corporate mentor from TI. Is Amber here?
She was not able to make it.
Okay. All right, next up we have pulse current source for ESP testing and semiconductor devices, so that's the TI project. And waiting to present next will be a Texas micropower project.
Was I in it?
Family
Was? Okay, cool.
design.
Good job.
Let's welcome our
Visiting, cheering on the kids.
testing group.